Yay, we're back and we're still here. We're still standing. Whether we're looking at academics or athletics, we have prevailed last night. And a lot of things went right. Got home early. Didn't have to sit on the side of the road. Or have to sit in Madison. Okay? So, with that, this is where we left off with your last, gosh, I don't know when it was last week, but we really talked, I want to say, a lot about this. And one of the things that we talk about when it comes to vocabulary that at some point, or I should say sometimes, it's just a lot more difficult using the author's definition or a rule book's definition as opposed to what you're actually doing. Okay? Because when we look at this, okay, can someone give me an example of an asymmetric reagent? Okay, so hydrogen chloride or hydrochloric acid would be that of an asymmetrical reagent. With that, that's where we said we wanted you to start. Are you always going to have a major and a minor product when it comes to having an asymmetrical reagent? The answer is no. But how is it that you know you're going to have two products when it comes to an asymmetrical reagent? Just in general terms. It would be very quick just to say that. Something about a double bond. So if it's in the middle, will that give you, it'll give you two products, but is it going to give you a major and a minor? No, it will not. Okay? So the conditions have to be just right to have a major and a minor product. And what happens is the easiest way to look at this, okay, what is that hydrogen looking for when that double bond breaks? Does it want to find some more friends where there were two hydrogens already, or just join where there was one hydrogen? You sure? Was it a late night last night? Shouldn't have been. We got home unless you're doing homework. Because we want to be here, right? No? Well, eventually we're going to have to find something called a JOB, and hopefully when we do that, we want to be there, we hope. And if I was to say something funny, we can smile. We're not going to break our face. I don't mind it. Okay? I mean, I think it's easier to learn when we're having fun. And no, there's certain times when a person doesn't want to be here. I mean, that could be any time. Maybe they're not feeling well, or maybe do we see the value in going over this? We hope, because that's one of the things we had talked about before. The idea that when it comes to scouting and it's after the fact, gosh, I wish we would have worked more on our passing or our setting or something like that, because it's too late. And we don't want that to happen for you when you go off to college. Geez, I wish we would have done a little better in high school. Not that you can do better or worse, but going back to when we said this, okay, the question was, okay, we'll just keep it simple. We'll just do, what alkene is this? Okay, it's propene. We know we're going to get two products. So the question was, when this breaks apart, where is that hydrogen looking? For the one that has two or the one that has one when that double bond breaks? The one that has two. Yes, not the one that has one. Because that's what Markovnikov's rule is saying. And sometimes I think it's just easier applying it rather than actually reading the rule or anything to that effect. I don't know if you could say the same thing for volleyball. If you look in the rule book, I don't know why you would, but maybe you have. I think the same could be said for that of basketball, how you determine what a travel is. And because I think sometimes it's not that the rules are changing, but I think it's easy to call it travel when it's actually not. Anyway. Okay, so what we see here then, when an asymmetrical reagent, we had hydrochloric acid or hydrogen chloride, asymmetrical alkene or propene. The major product H is being placed where there is the most already. So that's why you put it where there's 2 hydrogens around the first carbon as opposed to the second one. Okay, so then we talked a little bit about combustion, and that's an oxidation reaction. As you can see, you're applying more oxygen and the compound's becoming more positive in that effect. Because if we're adding hydrogen, it's a reduction reaction. So in this case, you were working on, you're balancing those chemical reactions. And for some of you, we hope we don't, it's not that you're going to forget that skill. You may just have to spend a little bit of time on it in 1 or 2 years from now. We just hope that information is there so you can recall it. So we could say that this comes full circle, okay? We're saying the carbon, the hydrocarbon, when it combines with that oxygen or becomes oxidized, okay, the carbons and hydrogens are attached to oxygen. In other words, carbon dioxide, CO2, and then your water or H2O. Okay, there's a reason that we got our books. We'll be using those in just a moment to make some sense of this. Okay, because I want to get through, oh shoot, we got the alkynes. Okay, there's our aromatics. Okay, won't spend a whole lot of time on here. And we know that there's a triple bond because our suffix or our organic family says YNE. I hope you don't have a whole lot to write for this. Yes? No? Just a little bit? Okay. So I want to get through this one and get to those aromatics. Okay, so with this here we see another reduction reaction. The simplest is without a hydrogen, just like it would be with the alkenes. You would also have to have a catalyst or there's no reaction. Hydrogen halides, which would be HF, HI, HCl, and HBr, and just the halogens in general. Remember, those are also that term diatomic. Is that the smallest gym that you have had to play in? Okay. Because this is maybe the the left-brained portion of myself talking to Ms. Carroll. Cubic feet wise, I think that's why I mentioned that was probably the smallest gym that you'd played in, because not only can you tell with our bleachers between the end lines, not the end lines, that go down the basketball court. What is there? Maybe 6 feet between there and where the bleachers start. So that's another probably extra at least 10 feet than what this other gym had. And then also extends on the ends, maybe, that might be about the same size, but especially up on the roof, okay? So I think obviously you would have noticed that the rafters set there come up at an angle. So the amount of cubic feet that our gym would have as opposed to theirs, and it probably felt pretty stuffy in there too. Yes? No? Maybe you didn't notice? Okay. And I thought, ugh, this is, and couldn't turn the fans on I think they did towards the end. I don't know, maybe you didn't notice, but, and maybe by that time, hopefully it had helped. Like I said, I really didn't notice, but bottom line, came away with a victory. It all looks the same in the books. Hopefully are we happy with how we got there? You know, like I said, it all looks the same in the books. Regardless, as we proceed forward, okay, when you look back at general chemistry, okay, what do you think was the most difficult portion of that year? I would say definitely in the spring. Would you agree that the spring was more difficult? And I don't think that would have mattered whether you were at home or at school. It's still more difficult. But so now we've isolated to the spring. What was maybe difficult in the spring then? .4 liters of a gas measured at STP, and then pressure times the volume of a gas equals the constant times the temperature times the moles of that gas, okay, or gas stoichiometry. That was probably the most difficult, and unfortunately you had to face that when we weren't here. But we made it through it. It all looks the same in the books, just like we're making a reference to last night. Okay, this is probably going to be, it's going to continue to get a little more difficult, which you've made a determination that you want to be in here, and that's good, okay? As long as we recognize if there's problems that we have, then we can address them, okay? Because aromatic compounds are not just ring structures, but they include benzene. Up until this point, we've been talking about aliphatic compounds, and those are just straight chains and ring structures. Aromatics, on the other hand, again, those are rings that include benzenes, so they're special rings. I suppose maybe you could say in a few years you've got, I don't know, a dress ring, a class ring, maybe even if you choose a promise ring, it gets changed to an engagement ring, and then finally a wedding ring. So then you would maybe say the wedding ring would be the most special and precious. Well, probably. So with that being the case, all the other rings aren't nearly as important as that last one, okay? Because that's when you would say you've made a commitment for that. So when it comes to these aromatic rings, it's the aromas that they give off, and that's why they're called aromatic rings, okay, or structures. Okay. So not only are there carbons we're talking about that can be single, double, but we're also talking about carbonyl carbons, your aldehydes, your ketones, your acids. Those all have carbonyl carbons because there's a double bonded oxygen somewhere in that compound. Okay? So with this, these are very different of what we call different types of chain structures because of the stability of this. And we'll look at some of these examples here in your book once we get this slide done, because there is, as you can see, quite a bit of information. Yes, it's at the end of this slide. We will stop and look in the book for just a moment. Okay, does everyone have this information that wants? Okay, go ahead, and we're not going to be reading a whole lot. Page 359. 359, please. And it's that 12.8, or that blue box. Okay, chemistry around us. Okay, so in that blue box, oddly enough, benzene is a carcinogen. You don't want to deal with that on your own. So if it's an aromatic compound, which it is, if I'm not mistaken, I believe benzene smells like some sort of cherry array. What do I want to say? Aroma. It was a very good cleaning agent, but unfortunately, it's toxic, so we don't use that anymore. But notice the same thing. When you go back to World War I, does anyone know or remember what mustard gas was? You ever hear of mustard gas? If I'm not mistaken, I think it's just that of chlorine. But when you combine chlorine with sodium, both of those are highly unstable and toxic. With that, you get a stable compound or salt. Okay? So when you change some of the atoms that are on there, you alter their chemical properties. Okay, so with that, page 359. Benzene is a carcinogen substance that causes cancer. But many derivatives of benzene are not carcinogens. Many compounds encountered in everyday life contain benzene rings. Prominent examples are many aromatic compounds found in flavorings and spices, such as the benzaldehyde in almonds, the vanillin in vanilla, beans, and the anethyl in anise seeds. Okay. Now, when we get closer to the holiday season, okay, has anyone ever made anise candy before? And that's what you'd be using, is this synthetic substance that would give it that flavor. Now, do you think, and the answer is no, you probably use some of these substances that have vanilla in it as a bug repellent. Has anyone ever done that? I think, I don't know, I didn't put much stock into this, but when you are working outside during the summer, you know, you got your choice of your deep woods off, okay? And then this, have you ever seen this substance before? Ace Hardware sells this, and I didn't put much stock into it until I saw some of the other guys putting this stuff on when we were going out to mow, and I thought, well, I'll give it a try. How many of you like this? Because it smells good. Yeah, it's got vanilla in it. Yep. So one of the things that typically, even in the fall, I put that stuff on every day because it's supposed to repel pests, but you people are still here, so. Yeah. I told a funny. We'll just wait till they quit rolling, then we'll get back to this. I am. Okay. And then one of the things, look at the upper right-hand corner, or aspirin, and then the benzaldehyde or almond. Okay. Set aside that they're both benzene rings, that's true, but why is that called benzaldehyde and aspirin has salicylic acid in it? What do you notice about the top? Okay, the carbon, it is attached to a double bonded oxygen for almonds, but what's that fourth bond? So one carbon, it makes a bond with the ring. It's a double bond oxygen, that's 3. That fourth one is what? What's that fourth one? Okay, I'll repeat the question in benzaldehyde. That top carbon, one is bonding to the aromatic compound. There's 1. It's got a double bond oxygen. There's 2 and 3. So where's that fourth one? Someone said it. It's a hydrogen. Yeah, that's it. Okay. Now, when you look at aspirin, how would you know that that's salicylic acid? Okay, same concept. One carbon is attaching to the benzene ring. It's got a double bond oxygen, so there's 2 and 3. So where's that fourth bond come from in aspirin? Not just hydrogen. Yeah, hydroxide or OH, okay? It's just little subtle differences like that, and I understand you got an ether that's attached to that as well, but it's just those minute changes that really alter the chemical properties of some of these aromatic rings. Okay, 2 other compounds containing the benzene ring are the female sex hormone estradiol and the synthetic painkiller aspirin. Okay, if you were to put estrogen and testosterone next to one another, they're, unless you are really paying attention, they're very, very similar. Okay, because they're built upon some of these aromatic rings. Okay, a number of chlorinated aromatics have been used as insecticides or DDT. That's a way before your time. But with that, do you know this insecticide almost wiped out our national symbol? Not the flag. What would our national symbol be? The bald eagle. And it really did not harm the adult eagles. It was the eggs that the young were growing in. It had a really negative effect on the shells of those, and would deteriorate them, and I think the incubation process, they would just not be able to be born alive. Okay, and exchanging electrical insulating fluids, PCB, DDT, and PCB are no longer used in the United States. However, in other highly industrialized countries because they are not harmful to humans and non-biodegradable. And are, okay, yeah. Nevertheless, the use of DDT continues in third world countries where people are more concerned about short-term starvation than about long-term health effects. And that is really unfortunate, but yes, that is, I would agree with that, yeah, it's probably cheap to make, cheap to use, but it doesn't mean that it should be used. And unfortunately, again, some of them countries use that. But one of the things that we are going to start talking about, okay, the top of 360 is the beginning of where naming some of these compounds, okay? Now, if I was to say acetylene, that's a common name. I highly doubt that anyone would ever say ethyne anymore. It's more so known as acetylene. So when you're looking at those, toluene is the common name, but it's also known as methylbenzene because there's a methyl group on top of that benzene ring. Phenol, okay, which is an alcohol because it's got an OH group, okay? So the suffix ends in OL, so yes, you know it's an alcohol, but it's also known as hydroxybenzene. And of course, we got COOH, which is indication of that of an acid, so it's benzoic acid, and then aniline, which is, as you can see, NH2. If you're not paying attention, it's very easy to get aniline mixed up with nitrobenzene, okay? Because there you got NO2 is nitrobenzene, and then aniline, which is NH2, okay? So this is one of them things to where the details it's a lot more detailed than that of general chemistry. Now, I just wanted to introduce some of those concepts that we're going to be going over because the more we spend time on that, I think the better off it will be for yourselves. And for our purposes, we use those common names, okay? Because I only think it's going to be more difficult for yourself if you keep using methylbenzene, hydroxybenzene. Just start wrapping our heads around that's what we're going to be using is some of those common names, and we'll dive into that tomorrow. Okay, so that's all I've got for today. And then I don't know, are we going to get to, no, I don't think we're going to quite get to the reactions, but I don't know why you would, but maybe on page 362 it starts to go through some of these aromatic reactions, and for those of you at the remote side, maybe you would, okay? And you've got those flow charts. We'll be using those in the near future, probably not this week, but certainly next week. Okay, that's all I've got. We'll catch up to you next time.